So, good afternoon, everyone. I hope you have a nicely temperate room where you're sitting in. Otherwise, sit back and relax, have a nice cold drink, and enjoy our session that we are here in the second webinar for Code for Earth. In the coding phase, my name is Atina Trakas, and I'm here with my colleague Esperanza, saying hi from Reading. And before we start with presenting the projects, let me say a few words about Code for Earth. So, just a few quick facts. You can find more information, of course, on the website. And if you need a deeper insight, feel free to connect with us. So Code for Earth is a key innovation action run by the ECMWF and is also supported by Copernicus and Destination Earth. Each summer, we welcome individuals and teams, developer teams from different backgrounds in earth sciences, computer science, and software development, and they work on challenges provided by colleagues from ECMWF and partnering organization. So essentially, it's all about innovation, collaboration, and open source software development. You can see, or maybe you know already, that most of the work is also accessible on GitHub. So feel free to sneak in to get an idea what is going on. The selected teams are granted a 5,000 euro stipend once they have successfully completed their projects. And this is a quick the timeline, the rough timeline of Code for Earth. So we started in March with the call for participation. And then end of April, we announced the selected proposals. And since May, all the 10 teams, they work with their mentors on the projects, they collaboratively develop solutions. And today we are in this phase. We have the second of the midterm webinars presenting what has been done by the team so far. So before we do that, I don't want to miss to thank our mentors for Code for Earth of this year. That's it's a fantastic amount of numbers, a fantastic amount of people and dedicated people, experts. And as mentioned, these are colleagues from ECMWF, but also from partnering organizations. And I want to thank all the mentors for doing a fantastic work with and around Code for Earth. So at this point, I would like to hand over to Esperanza.
Hello everybody. Last Wednesday, on 5th of July, the first session of this Code for Earth midterm webinars took place, and we had the opportunity to meet 5 Code for Earth teams and learn about the progress of the project so far. These projects are, you can see on the slide, benchmarking surface heat fluxes, diffusion models on weather bench, TropiDash towards a comprehensive tropical cyclone hazard dashboard. The fourth of the teams, the project was compression of geospatial data with varying information density, and the last one, atmospheric composition dataset explorer. If you missed the first webinar, there will be recordings available very soon. So you could watch the videos and get a grip of what's going on. But today we have the pleasure to have with us the remaining 5 teams. They will share with us an overview, a description of the projects, and also the first outcomes. We have fire forecasting, deep R, deep reanalysis, sketchbook Earth, illustrated climate chronicles, chat ECMWF, and tester RAG. At the end of each presentations, there will be a turn of questions and answers. So if you want to you want to raise a question, you can raise a comment. Please write your comments or a question in the Q&A chat. The teams will be willing to reply. And now I stop here, and I'm very pleased to introduce the first projects who are with us today, fire forecasting. Yeah, the members of this team are Robert Mewell, Timo Metz, Christopher Winkels, and Eva Marie Metz. This fire forecasting is the aim of this project is developing a framework to forecast wildfires in Europe using machine learning. So the floor is yours. Up to the team to when you're ready, you can start your presentation.
Thank you very much, Esperanza. Yeah, I'll share my screen 1 second. Perfect. You should now see my screen, right?
Yes.
Okay, then I'll give it a start. As Esperanza said, I'm Eva, hi, and in my group there are also Robert, Christopher, and Timo, and we are working on the fire forecasting project. To give you a little bit of context about our project, the context is in fire emission estimation, and there are, let me change the slide. Yeah. There are satellites which measure fire emissions or measure fires. For example, they measure fire radiative power, FRP, we will use this term in the future, like for example, the Aqua or the Terra satellite. And these satellite measurements of fire, they are then used by different models, which use the satellite measurements to estimate actually the fire emissions, for example, of CO2 or CO. One of these models is, for example, the global fire assimilation system, which then use, like I said, the FRP for its fire emission estimates. And here on the lower left, you can see tracks or the positions of these 2 satellites, and also the tracks they go around the Earth. And both of them, they are sun-synchronous satellites. And what you can see as a result of that is that they do not pass each point on the Earth that often. That means for each position on the Earth, they pass the maximum 2 to 3 times per day. And furthermore, another problem is that these satellites cannot measure fire when it's cloudy. So when there are clouds, they do not see anything. And both these discrete satellite overpass time and also the cloud coverage, that leads to the fact that for a certain position, there are large observation gaps. And with our project, we try to develop machine learning approaches to fill these gaps for one position so that you can have a whole time series for one location on Earth about the fire emissions. So the goal of our project, or the current goal, is to estimate 24 hours of fire emissions based on the 24 hours before the fire measurements we have there and other meteorological parameters. And what we want to produce, or our final goal, is to have a framework where we can apply different machine learning models to test which one is the best. And we then want to have an operational forecast, meaning that we do not only estimate the next 24 hours, but day by day, we can create a longer time series of fire forecast. What you can see here on the lower part, there's a sketch of the modeling parts we want to develop, or the programming parts we want to develop. So we first now had to deal with the data set and created a data set for our machine learning models. So we developed that, but we also implemented the machine learning models themselves and the training and test framework. Furthermore, what we needed was a data loader. And with all this together, we then could produce a forecast. And in the following 2 slides, I want to present you our data sets and some characteristics of our data set. And afterwards, Robert will continue and present you our first results. As you can see here on this map, in the middle of my slide, we focused on the Northern Hemisphere and satellite measurements on the Northern Hemisphere. And what we did now to create our data set for our machine learning models is that we selected different pixels, so spatial pixels, but also in time, when there was a fire within 1 day. And on the following day, we still had satellite measurements. So we selected each of these 0.5 degree grid cells and stacked them together. And this is somehow shown here below. So what we did is to not only select the fire pixel itself, but also the pixels surrounding it. And for the first 24 hours where was a fire, and the next 24 hours where we had at least 1 measurement. So we then get a 3 times 3 times 48 data set. And as we have 2 satellites, 2 times of it, and this then resulted in 10,000 or roughly 10,000 periods we selected for our training data. And we furthermore did is to shift all these 24-hour sequences by 1 hour, so that we had 24 times these 10,000 periods. We tried to somehow characterize these data set, and this is now shown here. I want to point out some special things. If you look at the upper left plot, you can see a histogram of the number of the selected pixels or the pixels in our data set, depending on the fire strength they show. And as you can see, the majority of the pixels do only have a small fire radiative power. So there are a lot of small pixels, a lot of pixels with small fires in our data set. If you now focus on the top right plot, you can see a histogram of how many fire measurements or how many hours of fire measurements do we have within the 48 hours. And there you can see that mainly we just have 1, 2, 3, maybe 4 measurements within this 48 hours of fire for the most of the pixels. And furthermore, what you can also see when you look at the third plot, so the lower left plot, there is shown how many fire hours are next to each other. So how long are the periods we have fire measurements 1 hour after the other without interruption. And there you can see that mainly we just have 1 or maybe 2 hours of subsequent fire measurements. So normally there's a fire measurement, a gap, and at some point later there's again a fire measurement, which makes it more difficult to have kind of a time series or a time development of the fire. And finally, what we also looked in before implementing the models was at our meteorological data sets, so which parameters could be interesting. And we had a look at the correlations, which you now see on the lower right. And as you can see, first of all, on the upper side, that vegetation plays a role, so over here. But what you can also see is that the boundary layer height, which somehow parameter which reflects whether we have a high pressure or low pressure system, is also important. And as expected, the temperature and also humidity, and a bit also the precipitation and velocity. And with this, we then selected which data we want to use in our machine learning model. And with this, I'm handing over to Robert.
Yes, as Eva explained, next slide, please. How our dataset looks like. We tried some algorithms on the dataset. The main challenge is that the input data is sparse because we have not complete coverage by the satellites, but we wanted to test the 5 algorithms on the data without regarding the sparse data at first, just to see the results, if it already works. And so what we did is we selected 9 variables from the data set for the last 24 hours and 24 hours in the future as features, plus the FRP from the last 24 hours and the fraction of area observed, so the satellite coverage. And what we predicted, the target was the fire rated power 24 hours in the future. The models were trained on the complete data set. So if there was no satellite coverage, the models should learn to output 0. But the evaluation was only where there was actually coverage from a satellite. The first model here is just the assumption that there's persistence. So this means that for the next 24 hours, it's just the mean value of fires in the previous 24 hours. And we see here from the 5 models, this is the most simple one, and then get more complex down to a multi-layer perceptron, which is a kind of neural network. And we see that in this case, the root mean squared error of the persistence is actually the best, and also the correlation. So this motivates for us to definitely implement a way to handle the sparse data. But this was just the first step, and mainly look at what time series do the models actually produce. So first we look at the ridge regression. And we can see here on the y-axis for all 5 plots, so it's 5 different feature and target sets. On the y-axis, the radiative power of a fire. And the left side in blue, we have the previous fire, and on the right side in orange, the target, in orange, and in green, the prediction. You can see here that the background is shaded in gray, where we have no observations of the satellite, so it's 0 in our data set. And we can see that at the right areas in the plot, on the left side, we have some signal, and on the left side and on the right side as well. And we see that the ridge regression, the linear model, is not able to predict any of this evolution because it outputs 0 for every step. But we can still look at the parameters of the ridge regression, which is a linear model. And what we see here on the y-axis are the 9 features that were used for the model. And on the x-axis, it's the time for the output prediction. So 0 is the first hour after first hour of the output to the 24th hour. And we see here in yellow, it's a scale of the importance of the features in the model. And we see that the mean sea level pressure, next please, has the highest importance, the most important feature, which seems reasonable because changes because it symbolizes a low or high pressure system. So it's an important indicator for the weather. And there's another interesting thing in this plot, and there's a gap in the 14 hours to 20th hour, and we don't know yet why there's this gap. And it might be something to do with the structure of our data set and the timing of the satellite measurements, if they come one after another. So that is something we want to investigate in the future. Next, please. And we can also look at the most complex model, this multi-layer perceptron. And here we can see that the model actually outputs for areas where we have a signal, actually outputs radiative power. So this is a good indicator because we have not really performed hyperparameter tuning for the models. And we also have not included the possibility to handle sparse data, but still the model already displays signs that it can handle the data. So we're pretty optimistic that in the future, if we implement the sparse data handling by creating custom learning algorithms, that we will be able to beat the assumption of persistence for the fires.
Okay, and with this, we're coming to the end of our talk and wanted to give a short outlook what we planned to do right now. So I think there are 3 main points. First of all, like you might have seen on the correlation plot, precipitation right now doesn't seem to play such an important role. And we expect that this might change if we do not look only at certain time steps, but rather also the time development, so the time derivative, because actually a fire stops when it rains. And we also want to identify nonlinear correlations between the parameters. And like Robert already mentioned, we want to improve all our learning algorithms and also include hyperparameter tuning. And finally, what we also want to do, and what is shown on the right side in terms of satellite measurements, we have these nice time series, for example, over a month. and we do want to expand, therefore, our time series not to only have 2 days, but rather, for example, look at a month, like shown here on the right side. With this, thank you very much for your attention, and please just write your questions like we said in the chat. Thanks.
Thank you very much, team. Impressive results, so well done. We have a question for you. So I read it loudly for you. Why do you think the correlation with surface pressure was low? Do you want me to repeat?
Maybe once again.
Yes, you can also read it in the Q&A. Why do you think the correlation with surface pressure was low?
Okay, maybe this addresses because, like Robert said in his model, it showed that the mean surface pressure was correlated. We don't know exactly. I mean, that will be also part of the further analysis, I think, why certain parameters show correlations and certain don't, like I mentioned, for example, for the precipitation, but then also for the surface pressure. Yes.
Thank you. Thank you very much. So now it is time to present the second team, Deep Reanalysis, which is they are with us. They are creating a machine learning model that can generate high resolution regional reanalysis data year-of-it. So with us is the members of these teams are Antonio Perez and Mario Santa Cruz and Javier Diez. Representing the teams, they are with us, Antonio and Mario. So the floor is yours. When you are ready, you can give us an overview of your project. Thanks.
So thank you, Esperanza. This is the presentation for the status update of the project Deep R. We are going to talk about what the project is about, our methodology, also the implementation in a Python package, and the main results that we have obtained till now. First of all, we want to talk about the members of the team. We are all of us from Spain, from Santander. We work in Predictia, and a spin-off from the university here in the community. And Javier works for the Institute of Physics of Cantabria, which is also related to the university. The challenge is mainly proposed to downscale the coarse spatial resolution data from ERA5 to a higher spatial resolution like the one that Terra proposed. We are going to do this through the use of machine learning techniques. And for those who don't know what is array analysis is a comprehensive reconstruction of historical weather, assimilating data such as real observations, satellite data, and so on, combined into a numerical model. These reanalyses are really important because they provide consistent information of historical weather conditions, and they serve as a very important resource to those who have to make the decisions in our society. Also, it is important for assessment of climate projections or numerical weather predictions. But there are, for those who are familiar with the reanalysis data, the ERA5 global reanalysis is one of the most commonly used reanalysis data sets, and its resolution is around 31 kilometers, So in many sectors, they need a higher resolution to capture the finer scale details, which are critical for localizing weather patterns, and also they enable to understand the more complex atmospheric processes um, that are inside the models. So the project motivation is to go from a coarser spatial resolution from around 0.25 degrees, like the ERA 5.1, to a higher resolution, like the Serra 1, with 0.05 degrees. This issue is illustrated in that image where we can see that ERA 5 do not depict pretty well the Pyrenees area here in the Iberian Peninsula. As a first step for the project, we have defined a smaller domain in order to reduce the data complexity during the development stage. We have taken an area where we consider mountains like the Pyrenees area, also a land-sea transition like the one in the Mediterranean Sea. Also major cities like Madrid, Barcelona, Valencia, and large lakes that are located all over the north of Spain and also in the Mediterranean area, and several islands corresponding to the Balearic Islands. And just to wrap what I said before, the main purpose of the project is to design a deep learning algorithm with models and architectures that Mario is going to explain later, to generate estimates with the same resolution as Terra.
Hi everyone. So I will talk now about the methodology we are implementing. We have proposed an AI-based solution for generating these high-resolution grids. In particular, during this challenge, we are researching about the use of diffusion models because they are now the state-of-the-art in image generation tools like DALI or Midjourney that all of you may know. And they have like the main advantage they have are like its learning capacity, the extrapolation to new data, and also the realism of the predictions. Now I will briefly explain how these models work. During training, you just try to add noise to the target images until you get random noise. And during that process, you are training a neural network to learn the added noise at each time step. So during inference, you can apply iteratively this neural network to the noise, random noise, into a final grid, high resolution grid. But these techniques has also important drawbacks that are mentioned below, and we have tried to face. For example, the training efficiency and the scalability of this model. To face this, we first reduce the domain area, and we are also considering the implementation of latent diffusion model to what we have implemented a vector quantized variational autoencoder to work on the latent space of the grids instead of the full grids. We have they also have long inference times. To this, we have implemented state-of-the-art noise cellulars to reduce these sampling steps during inference. As this technology is very new, a lot of architectures and schemes are being published. So it's important also to tune the networks. And finally, another point of interest is how you add additional constraints or covariables to this dataset, as it can be the hour of the day or the day of the year. So here, some of the plots we consider during validation. Some of them are very general, like the error matrix or error square, but there are also more specific validation, limiting to specific dates or areas of interest that can tell us how these meteorological predictions work in comparison with Sierra. We have implemented a Python package under the common repo that is tracked there, deepr, and we have considered a pipeline that does all the process from dataset preparation, the architecture, the model architecture loading, and also it trains and saves the model. It is prepared to be trained with CUDA, so it's very efficient. It also implements the validation. This pipeline can be run all in once or only the validation if you want to validate a trained model. We use files to configure the pipeline, like the ones you see here. And now we are presenting some of the results we get. Just briefly for the diffusion model, the first one we trained, you can see the samples comparing the prediction with the target. The target is the second row and the prediction is the third one. The border, you can see that the model is clearly learning something, but it doesn't get the high resolution structures from Sierra. Here we also include another metrics like the large function over training or additional metrics. And we also train a regular neural network for downscaling the ERA5 directly to Sierra. And we can see that the difference with the cubic interpolation is very small. The general improvement is around 5%. So there is not much improvement over with these type of networks. You can see that this network has a lot of improvement over the coast, but yeah. Here some additional error plots of the baseline method against the neural network for a given sample. Just as next step, we are training now a diffusion process, but guided with the upscaled ERA5 image instead of coarse ERA5 grid. And then we want to train the latent diffusion model and other options like the percentage there. So at the end of the project, all models will be openly available through Hugging Face. You now can check the repos to see the model checkpoints and also the training metrics and validation plots. So thank you very much.
Thank you very much, Antonio, Mario, for your results. We are looking forward to the second part of the coding phase when you finish your exploration. Yeah. We have a question from Florian Pinault. Which metric did you use for the training? Do you expect the choice of the metric to have a strong influence on the results?
For the diffusion model, we use L1 loss. We don't expect much difference comparing to L2. In the normal neural network for super resolution. We use L1 loss with additional terms to evaluate the spatial consistency that are typical in these super resolution tasks.
Thank you. We have another question from Noelia Otero. Did you use any pre-trained model? And as an input, did you include orography?
No, we didn't use any pre-trained model. We have implemented the option to pre-train these models, and the idea of training a regular neural network was to use it as an input for the diffusion process, to guide the diffusion process with an estimation of the high resolution grid. We don't include orography now in the models because we are considered static images, but we are, for example, including it in the validation step to see the difference between different orography levels.
Thanks. We have the last question from Kiko Correoso. Do you need just one variable for the downscaling, or are you considering more than one and different levels?
For during this challenge, we are just considering one variable. If we would have time, we would like to try considering more variables or also more time steps of the same variable. But now we are just considering one variable.
Thank you. Thank you very much, both of you.
Thank you.
Thank you. Now is the time from our third team, Sketchbook Earth, Illustrated Climate Chronicles. This team, the aim of this project is to develop Jupyter notebooks to illustrate climate stories. The members of this team are formed for two members, Nicholas Rieger and Nikos Mastrantones. Nicholas is with us today, so I hand over to you. You can enlighten and tell us more about your project. The floor is yours.
Yeah, thank you for the kind introduction. And good afternoon, everyone. Happy to be here as part of Sketchbook Earth, our project that includes my colleague Nikos and myself, Niklas. And before we dive into the topic, I'd like to draw your attention quickly to this beautiful visualization. I think I really like it. I think it's very impressive, regardless of whether or not you are familiar with climate science. And when I first saw this beautiful visualization, I could not resist trying to understand what was going on there. So I went to the website of NASA's Scientific Visualization Studio, the creator of this animation, to find out that, yeah, I don't want to ruin your curiosity. So I invite you to have a look for yourself. But the key message that I want to transmit here is that climate science communication, and specifically climate science visualization, is an important tool we need in our future path to combat climate change. And indeed, climate change communication matters. So here, as a recent study analyzed how much people know actually about climate change in different countries. And you can see here in red, like where people know more, and in blue, where people know less. And I think it's not too bold to state that the pattern of knowledge about climate change pretty much coincides with wealthy nations, where climate change communication is already an integral part. There's lots of funding available for driving efficient communication campaigns and so on and so forth. Well, even though these well-informed nations may not necessarily be more active when it comes to real climate action, but anyways. And if we now zoom into Europe, I think the Copernicus Climate Change Service, in short C3S, is a prime example of climate change communication. So I think you've probably come across their work at some point, but just in case, here's a quick overview of their climate intelligence reports. And I think what's probably the most well-known service are these climate bulletins, where they present every month the climate conditions around the world. And in addition, they also provide on an annual basis the European state of the climate, short ESOTOC, the long-term evolutions of certain climate indicators, and also annual global climate highlights, where they really go into specific events like heat waves, floodings, and so on and so forth. So let's take a brief look at the climate bulletin from June 2023, so previous month, which depicts the global surface air temperature anomaly. And now I would like to take a step back briefly and just think about for a moment who benefits actually from these information. So who is like on the receiver's end of that information? And actually here introducing the target audience, it's quite large. So it encompasses a broad spectrum ranging from climate scientists here on the left-hand side, educators and students, journalists and media professionals, environmental consultants who ultimately will inform policymakers and also general public, so like hobby scientists. And to illustrate here, let's consider briefly like the journalist reporting, or let's consider a journalist who wants to report on the recent heat waves in North America. And while the climate bulletin is informative, the information is only available as a static figure. So if he now wants to make a story about the temperatures over North America, he basically faces the issue of reproducibility and transparency. So how can he reproduce these images? What are the steps, really step-by-step necessary? What is the pre-processing? So it's not really clear, not really transparent. And this is where our project comes in. So our goal is to provide open solutions to reproduce these figures. For that, we only use open data sources like Climate Data Store, Atmosphere Data Store, Marine Data Store. We rely on open infrastructure like Jupyter Notebooks and Google Colab, and open software, specifically here for us Python, and very well-known Python packages like Xarray, Matplotlib, Cartopy. And secondly, we also aim to be transparent by providing tutorials that guide the users on step-by-step really how to access the data, how to pre-process the data, and finally how to visualize the data. And here on the right-hand side, you can see one of our first results. So this is a tutorial dealing with the greenhouse gas concentration evolution over the last 20 years. And our goal is, throughout these notebooks, to strike a balance between simplicity and flexibility. So we want to make them as user-friendly as possible, but at the same time adaptable so that people can modify them to their specific needs. So that means you will find throughout the tutorials individual cells that allow the user, for example, to define his or her region of interest, or to define the climate reference period that she or he wants to use. So to briefly give you an idea of how the results look like, you can see here on the left-hand side the greenhouse gas concentration of methane and its evolution as shown in the original C3S intelligence reports. And on the right-hand side, you see the result of our reproduction. So you probably note already that the style is different, but we have decided to use a Matplotlib style sheet that streamlines our visualization so that the output of all the visualization is very similar. But the underlying data is the same. So as for our future steps, we are currently working on a series of these example notebooks. Our first one dealing with greenhouse gases is under final review, and 3 more on temperature, sea ice, and sea level are in progress. And we also plan to provide 2 more notebooks about hydrological variables and river runoff. And then in the second step, we're also working on creating animations of selected variables, because we believe this is always they play like a significant role in climate science communication. So here's a sneak peek of an animation we've developed. And finally, we will also deliver a notebook on how to derive large-scale patterns like ENSO and NAO. Yes, and if you're interested by our work, or you have feedback because you are by chance the journalist from North America, then please reach out, get in contact with us, and explain us also your needs. You can follow our progress here on our dedicated GitHub repository. And that's it. So thank you. And I hope to see you in person in September.
Thank you. Thank you very much, Niklas. It's very interesting and also very, very useful for all type of audience, for training as well, or tutorials. And do you have something in mind when you finish this project? So maybe a follow-up, or you have some...
To be honest, we have not, Niklas and I, we have not really talked about it. So since it's still like a bit to go with the project, we will discuss this with our mentors. Yeah.
Good luck. Very, very well done. I don't know if someone... Oh, there's a question. Maybe I missed something, but how can CO2 sources and sink be established? Maybe from data provided by countries or industries? I don't know if this question is related to this.
Oh, yeah. I
Yes?
see. I mean, at that point, I actually, to don't tell you any nonsense, I would really invite you to check out the creators of this animation. So if you just Google NASA Scientific Visualization Studio, will directly fall onto this. And you can then check out the underlying publication, which they have used for creating this animation.
Thank you very much. If there is no any question, the floor is yours, Adina. You will present the next day.
Yeah, thank you, Esperanza, and thank you for the teams for presenting so far. It's really interesting, you know, even as Esperanza and I, we are coordinating Code for Earth. It's nice to have this inside view into the projects. So it's my duty now to introduce the next 2 presentations, and let's start with Chat ECMWF. So, and the team is Piero Ferrarese and Giacomo Bigan, and as you can see, they're both with us. So I hand the floor over to you. Our chat, yeah, just a few words. So the aim of this project is to develop a search engine that can reply to a number of queries related to this ECMWF datasets, charts, and documentation. So, and the insight comes from Piero and Giacomo.
So, thank you very much for the introduction, Athena. So, yeah, in our challenge, we are developing a natural language search engine, and the aim is to improve the discoverability and also the usability of ECMWF datasets, graphical products, and documentation. So let me start from the current state. So ECMWF has a very large number of data sources, and they are distributed on many different platforms. So currently we have the Confluence knowledge base with a lot of very useful information We have web content also distributed on different websites, GitHubs. There are many different data APIs, and there is the charts API.
Sorry, Piero, to interrupt you. Someone is commenting that the image is frozen. Can you try like browsing again your pages?
Like this.
Okay.
So we are at the slides, the current state, various ECMWF data sources. Can you see this?
Okay. Yeah, for me it was fine, but we received.
Yeah, also here on my other laptop, everything is fine. So maybe.
Okay. Sorry to interrupt you. It was just because of the comment, but I'm sure.
No problem. Yeah. So yeah, that's the current state. A lot of useful information spread on different platforms, and so like what we would like to do is to improve the discoverability, improve the usability of these data sources, and also maybe as final goal, enabling mixing and comparing data from different sources. And so what we propose as a solution is a chatbot, which makes possible to interact and to discover ECMWF resources in a conversational way, which is much more immediate. So here we have a screenshot of the final product, but we also have a demo later in the presentation. And our goal is to provide easy access to the data, is to have a chatbot which you can interact with in a conversational style, making API access very simple. And also we would like to have a unified interface for all data sets, content, and knowledge bases. So let me just spend a few words on the technology which is needed to get there. And so like here, of course, this is a very broad and very very active field, but I think that it is interesting to spend just a few words here. So how is it possible to design algorithms that can understand human language and that they can reply also with human language? Since the 90s, the so-called recurrent neural networks have seen a lot of success in maybe in translating from one language to another language. However, our NNs are limited by a rather short memory. The real breakthrough happened in 2017 with the introduction of transformers, which have a new mechanism called self-attention, which allows to have a much longer memory, so capturing the local and the global context. And this transformer is the T in ChatGPT, and so well, was instrumental to the development of the instruction-tuned chatbots that we have today, ChatGPT, and also many others. And the second very important piece of technology that we are using for our product is vector database. So what happens usually in most chatbots is what happens in the figure on the right on the bottom. So is that you have a query, you are sending it to the chatbot, and the chatbot will give some answer. However, it is possible to supplement this feature with a vector database. So what we do is that we map the query to a certain vector, and also we convert all the documents in some knowledge base, in some wiki, also to vectors. So we can compare the vector representing the query to the vectors in the knowledge base using some measure of similarity, and we can form some context, maybe selecting the 3 most similar documents or the 10 most similar documents. And so what we have in the end is that we are providing to the chatbot the original query and also some content coming from the knowledge base. And this is very useful because we can also use some private information maybe that we cannot use for the training of the chatbot, or we can also use some updated information which was not available at the time when the chatbot was trained. And so with this workflow, it is possible to greatly enhance the capabilities of a chatbot.
So I'll move on explain the second building block of our solution, which are tools. So tools are general instruments in the hand of the chatbot. For example, if we have an API specification that comes in some structured form, for example, Open API standard or XML, so we can build in simple ways, structured prompts that are supplied to the large language model. So through prompt engineering, we can actually teach the large language model how to interact with these APIs in order to retrieve data or information. So within our tool, we have embedded 2 different APIs. One that returns the meteogram for a particular location, and the other is the general API charts, which comprises more than 300 different endpoints with several different chart products from ECMWF. So we here on the right picture, we see, for example, an example prompt, which it's typical to be used within LLM development, with which one can allow the model to understand how to interact with APIs. And tools exist for very different type of tasks, not only APIs, but also programming languages, many other things. And actually, so right now, the market for this type of model is such big and new that every now and then a new tool is coming out, And so we have this model, so actually we employed ChatGPT, and we'll spend a couple of words later on open source models. And we can, so we built an interface, as Giacomo said, in order to interact with that. And we like now to show you a couple of examples. So I kind of go live now and show you directly the interface, that is the one that you actually see. So it's very simple. So we can just put some text in it, and it will actually work. I'll put some here. There's always some disclaimer to say, because as you know, the ChatGPT models has some. So it's not really stable in the sense that it can yield different answer to very similar queries, but actually, so this is working now. You see, we ask for the meteor for Venice, which is the place where we are based, and here the chatbot replied with a link to the endpoint where the meteogram for Venice is stored. As you can see, there's actually the city, written down. So actually the model needed to convert the city to a latitude and longitude point, thing that actually ChatGPT does great at. And this is, total cloud cover, total precipitation, 10-meter wind speed, and temperature, which is a standard meteogram from ECMWF. So it's a forecast for the coming 10 days. So let's move to another type of question, which is how to access charts, And then we ask a chart of mean sea level and 10-meter wind over Venice for tomorrow at 12, And even here, all the different endpoints that ECMWF has not always all these endpoints has the same parameters to be used. So there's different projections, different time that are available for different APIs. But also here we solved nicely, and we got, so the query was, let's say, pretty defined, 10 meter winner means sea level pressure, which is a product well defined. The date is tomorrow at 12, as we asked, and the area is Southeast Europe, which is the projections available within this type of chart that is closest to Venice. No, and this is the second part of what we have seen. Now I'll put a third question, which is more general, related to knowledge-based retrieval. Here we, in the current version, we retrieved on the database in the way Giacomo explained before, the top 4 matching documents, and the model does a summarization of the content from all these 4 documents, and then we display also directly the links. So we ask, what is EC codes, which is not, maybe for non-technical people, not very famous. EC codes is a module for working with group files, which are gridded files that contains weather data. No? And here we have, for example, the different links that were found, something from Confluence rather than, an HTML file from GitHub from EC codes, together with the README, for the repository. So these are probably the documents that match most the query that we asked for. So now I'll probably need to get back to the presentation, and yeah, so these were the examples that we just show. These are other pictures that other charts that you can ask. For example, carbon dioxide is another product in Southern America, or other different knowledge-based questions. So actually, we also put, maybe I haven't shown, we also put a couple of buttons to send some feedback, because that will be important, for making parts of our experimenting further, and also gather some data. Now we can save queries, and now in a very simple way, like okay or not okay, and but through this we can actually also gather some feedbacks over how good an answer was. So let me move back to the slides. So we have some comments on open source models that we actually, so we spent some time inspecting these models, and because they come with some advantages. For example, they're self-hostable, they're private, they're probably more efficient because we could build a smaller model solution if working. They come also with some disadvantages, because we tested very different models, and we started from the smallest one, and we see that actually to replicate ChatGPT, or at least a fraction of ChatGPT efficiency in handling all of these, we still need quite some infrastructure in terms of GPUs, and therefore there's some quality and performance issue. But yeah, so we are confident, that in the way this field is going, that in some months we will have more solutions that also are fully open source. Then last, we have some outlook on what we are willing to do in the coming period till the end of the Code for Earth. And we need to add the data API to the model, which is through which we can actually also get code for accessing particular data, similar to what we have done for the charts, but asking a proper query for the data API. Then we need to improve the error handling of the chatbot interface, and we need to work on the stability and reliability of the model. So basically what are called nowadays hallucinations, because now and then, even though we ask through prompt engineering to stick to the task that ChatGPT was given, we still have by now and then some hallucinations. So creating new random parameters not existing on on the API, even though we specified exactly which one to use. But so these are a common issue that people are having with these tools, no? And we would like to have some like a crowd experiment in which we give the chatbots, so the interface you just saw, to many different users, collecting feedbacks, and then eventually employing also this data set we can create through this experiment for further fine tuning or improving the tool. So that was all from our side, and thank you very much for listening, and we'll see you in September.
Yeah, thanks a lot, Piero and Giacomo. Very interesting insight. I'm a big fan of the image, by the way. So, but we have two questions for you from an anonymous attendee. The question was, what is the chatbot? Is this the well-known ChatGPT?
Yeah, so we also probably at some point at the beginning we weren't saying that, but yeah, so we employed finally ChatGPT. And to reply to the second question, which is, do you use GPT 3.5 or GPT-4? I think we use GPT 3.5, not yet the GPT-4. Yeah. We don't use actually OpenAI embeddings, but normal sentence transformers embedding for the data that we have that we have employed and loaded to the vector databases. And yeah, plan to move open source. I think the slides that we presented before was I hope that it was answering. Yes.
Yeah, like if I can just add
Sure.
a little bit of information, like well, so what we saw experimenting is that for the embeddings, even open source ones work very well, the one from the sentence transformers library. On the other hand, when it comes to language model, GPT 3.5 or GPT-4 even better, but we were using 3.5 for this example, is still performing much better than Llama or other open source alternatives. So, but the field is changing so rapidly that maybe before September there are even some new developments. So.
Yeah, it's a very fast community and well, science. There's a last question for you. Can this be used to improve the documentation by asking and votes? Are there any inconsistencies in the documentation about X or XYZ?
We haven't tried this, but actually what I can say is that, for example, the web content is a summarization done by ChatGPT of the web content, so performed by one of our mentors, which we thank. And so, yeah, I don't know if this answers your question. It's probably an improvement from the point of view of how the text is clean and on the general type of content. But yeah, we haven't tried exactly what you're asking for.
But it's a very good,
yeah. So maybe by September. Okay, thanks again, Piero and Giacomo. Very nice presentation. And I would like to move to our last team for today and also for the series of the midterm webinars. That's the project Tesseract, with the aim at implementing a model output approach and deep learning approaches for post-processing and downscaling using residuals. It's also a regional reanalysis project for Europe with machine learning. And that's a big team with Irene Schicker, Sebastian Lehner, Markus Dabernik, Toni, Jolina, Alexander Kann, Konrad Meyer, Petrina Papasek, and Matthias Schlögl. And today we have Irene and Sebastian with us, if I'm correct. Yeah, yes. Irene, I hand over to you.
Thank you, Tina, for the introduction. Yes, so we are also part of this downscaling challenge, and not moving. Yeah, so our team consists of metrologists, and climatologists, and we're both working in more post-processing tasks. And our mentors are Mariana, Matthew, Andres, and Cornell. And yeah, I'm not going to spend too much time on explaining the downscaling challenge. I think the Spanish colleagues have given quite a nice overview of what the task is. And we have a bit of different workflow. So our approach is that we try to not use the classical normalization, but rather try to perform the downscaling on residuals, which means we first calculate the climatologies of both input and output, and then we calculate the residuals compared to the climatology and add some sort of seasonality. And this is then used in the downscaling. And we have three models or three approaches. One is called SAMOS, which is based on this idea of standardized anomalies and is a more statistical approach in downscaling. Then we will use a unit with adapted loss functions and a conditional GAN. And this will result in error downscaled, and then we have the verification. So to give you an idea of how this works with the residuals, here you see for one grid point for the whole time period of the training, the temperature curve, and this is what it looks like. And then we add and fit the climatological model, and this is done per time of the day we are downscaling and per pixel separately. So we calculate this really a per pixel model. So we have this fitted climatological model and then calculate the standardized anomalies. And this is what you get as anomaly. So you have this for every day and every hour used in this downscaling issue, you have a separate anomaly, and for every grid point, this you feed into the respective model, and you also train on standardized anomalies. And to get something meaningful back, you add the mean and the standard deviation to the anomaly forecast. And right now we are finished with the SAMOS approach. And SAMOS is based on ensemble model output statistics, which some of you might know. And the standardized anomalies also allow us to have this single linear regression for the whole domain. And on top, you see what is the ground truth. This is the error 5 input. And this is the mean predicted SAMOS output and the standard deviation. And this is for a case, in-sample case in January, and we have the same for an in-sample case in August. And the advantage of this approach is that you, in theory, can also draw ensemble members based on the ensemble mean and the standard deviation. And we did an in-sample verification. The out-of-sample verification for the test period is not yet finished. The colleagues didn't manage before holidays, but next week we will start the verification for the test period. But what you can see in the in-sample verification is that the SAMOS approach does already reduce MAE and RMSE quite a lot. So we have an improvement of above 20% here. And the results also suggest a good calibration. So moving to the next method, we aim at using a classical unit approach. We use here 5 input features: the temperature residuals, topography, and land CMAS information of the course, and the fine resolution. We implemented 4 different loss functions, or actually used 4 different loss functions: MSE, MAE, and we also look at inversely weighted MSE and inversely weighted MAE. And we started with 2 model strategies. because of the resources we were using first, we are not able to use the domain agreed with the Spanish team. So we had to use a sub-windowing approach. But we moved now to a different computing platform. So we will use the full agreed domain in one go without the sub-windowing. So what we also do is, or what I also did is looking at these residuals. And if I need to apply some sort of normalization as well. And these are residuals for selected dates at 0 UTC. And what we see is that we actually need to apply an additional normalization of the input data. And we will do this with the min-max normalization. In case you wondered, there are some strange features still here, and I need to look a bit more into detail if it's related to the calculation of minimum and maximum, or if the issue is somewhere else. Yeah, and what we also do and did implement are 3 different types of unit, which are slightly different in the configuration. So one unit is fit for this sub-windowing approach and used exclusively for this sub-windowing approach. And the other units differ a bit in terms of how many layers they have, what skip connections are, what weight initialization they use, and so on. And what we also look into is if we're going to use the high resolution topography as additional target parameter or not. And this was shown in 2020 or 2021 in the paper that adding the topography did in fact improve the downscaling results. So this is still on our list to look into. And what we have right now for the unit is we have a main code which calls either training or prediction. We have the normalization and some plotting functions in the utils. We have a generator depending on what type of unit and what type of approach you're using. You either have a generator for the sub-windowing and then a generator for the full domain. We have the custom loss function specified in a separate file plus the units. And you call this model with arguments in the command line. And now I hand over to my colleague Sebastian, who will explain a bit the GAN approach.
Yeah, so for the GAN, we're currently in the implementation stage, so no results to be shown yet. So many of you are probably aware that there are different like ways how you can formulate GANs. There are a lot of different conditional GAN architectures that depend on what input you have or what kind of problem you want to solve. And the usual or a very neighboring approach to how downscaling, like from a phenomenological point of view, works is similar to how in computer vision, when you have a super resolving problem or where you have an input picture in a low resolution and you want to increase the resolution with increased details in terms of how certain features in images are represented. And the specific architecture that we use as basis here is the SR again, the super resolution GAN, or more specifically the enhanced super resolution GAN, which was just those are just a couple of subsequent developments that improved on their predecessors and improved the high resolution details that these certain GANs produced. And the input features and the setting in general, I don't read all of these points again because they are similar to the unit basically. So similar with the upgraded computational resources, we can tackle all of the domain at once, and we probably don't need to think about sub-windowing or patching within the model, which makes it easier. Yeah, and what we also play around, what we want to play around with in terms of the conditional is that you can use different input features, input images, like you would normally expect an input feature to be. But the special thing or way how conditional GANs are structured is that you can also supply conditional images into the model, which is input separately than the normal input features are. And this allows certain characteristics to be better captured. And what we want to experiment with is also that we don't use the high resolution topography just as an input feature, but to use it as a conditional. And yeah, the results, again, we are currently in the implementation phase, so we don't have any results to show yet, but we are very much looking forward to the next couple of weeks where we will get the first results. Yeah, next page. And this is already it with our short overview. So again, here we just have a couple of work steps listed. The SAMOS, the first modeling, our base that we referred to is finished, except for the out-of-sample validation. UNet is in its refining steps, and GAN is ongoing or in the implementation. And verification is obviously a parallel process that we will do until the very end. Thanks for your attention.
Thank you very much, Irene and Sebastian. Interesting insight also, we had both ERA 5 or downscaling projects here in the session. And looking at the Q&A, there is a question from Florian Pinot. Why is it easier to train with the Wasserstein loss, faster to compute?
So usually in the very standard formulation of GAN, you have, like, for example, cross entropy that you use as loss, and you can run into these issues when you have the two distributions of the fake or of the generated fake distribution and of the real value distribution. You can have the issue that those distributions don't overlap and certain losses then don't have a gradient, and then you can't really perform gradient descents in the whole training process. And Wasserstein loss solves this issue because it can always generate a difference between distributions to formulate it in an easier way. And if the distributions don't overlap and are further away, then it will still just increase in value, basically. So you won't run into this issue of a zero gradient.
Okay. Thanks, Sebastian, for answering the question. I don't see any other questions, so a round of applause also from me to all the teams and presenters. Let me share my screen quickly. So, because we are coming to an end of today's session, here we are. So we heard today from Fire Forecasting, DeepR, Sketchbook Earth, Chat, ECMWF, and Tesseract. And that brings me to the last slide, or a lot of us mentioned, September. September is an important date for Code for Earth, because on the 20th of September, we are celebrating the completion of the program. So this is where all the teams come together, they showcase and present their documentation, and that event will take place in Bologna and is a hybrid event. And hybrid means that everyone who is interested can participate online in that event. And this is where all the 10 teams, 5 you heard today and the 5 from last week, will present their solutions and how they came to the conclusions, and maybe do a little bit storytelling about their travel through the Code for Earth program. So stay tuned. There will be more details, I think by early next week on our website. And then you can also register for the online participation. Good. I'm looking at Esperanza. Is there anything else we need to mention? You're muted. So Esperanza, you're muted.
Sorry. Yeah. No, I think we're down on. I want to repeat the congratulations to all the teams, these teams, and the 5 teams that were with us last week also.
Okay, then thank you very much. Thank you very much to everyone. Have a nice afternoon or morning wherever you are, and hope to see you soon. Thank you. Bye.
Thank you. Bye bye.
Thank you, everyone.
Thank
Bye-bye.
you. See ya. Have a good day.